Thank you so much for coming to my qualifying exam, and the topic of my presentation today is data-driven approaches to resolve the feedback process driving a system over multi-spatial and temporal scale. So I will first introduce the data-driven method I use called transfer entropy and the lasso regression. Then I will discuss how to comprehensively use these two methods, and I will briefly introduce 4 research projects of the complex Earth system over multi-spatial and temporal scale. As we know, the Earth system is characterized as a nonlinear, complex, and dynamic system, and the coupling feedback process among the variables change depending on the stage of the system and the spatial and temporal scale at which the system is studied. So understanding the underlying feedback process could reveal the process network of the complex Earth system and identify the major and minor factors in terms of dynamic and multi-scale. Data-driven approaches such as transfer entropy and lasso regression take the advantage of the information theory and the statistical learning, as well as resourceful data inputs with high spatial and temporal resolution in this big data area, which offer a potential way to solve the problems above. So let's start with an example. The ocean climate system is a complex Earth system. The El Niño is one of the most famous events in this system. So the anomalies in sea surface temperature in the Pacific Ocean will cause the precipitation pattern change in the United States. So I will discuss why data-driven approaches could resolve this nonlinear, complex, and dynamic process. Claude Shannon introduced the idea for communication and his new idea of information theory, now fundamental to all things computational. Commonly, we think the entropy as the amount of disorder in a system, and entropy is the average uncertainty in value of a sample of a variable, equivalent to the average information required to determine the value of that sample. So let's think in 3 scenarios. First, the variable is constant. There's no uncertainty to this variable. People don't need to ask any question to determine the value of this variable. So in this case, the entropy is 0. Second, the variable is uniformly distributed. Each value has equal probability to occur. The uncertainty of this variable is high, so does the entropy. Last, the variable is normally distributed. People would prefer to ask questions about the value with higher probability than others, which lower the uncertainty of the variable compared with the previous scenario, so that's the entropy. And let's move a step forward. We have 2 variables now. The yellow circle represents the uncertainty of climate index, which could be the sea surface temperature anomalies or sea surface pressure and so on, denoted as X here and later in this presentation. And the blue circle represents the uncertainty of the precipitation in the United States, denoted as Y. The mutual information could tell us how much information is shared between X and Y. It also tells us, given the knowledge of X, how much uncertainty of Y will be reduced. So the mutual information is shown as the overlapped region. Okay, here we have the dark blue circle represent the uncertainty of the current state Y, and the light blue circle represent the uncertainty of the history of the precipitation. We will call it the history of Y or past Y in this case. And the yellow circle represent the uncertainty of history X or past X. And the mutual information between current Y and the past X measure the degree of uncertainty about current Y resolved by past X. And in our example, which means given the history of sea surface temperature, how much uncertainty of the precipitation will be reduced. And the mutual information between current Y and the past Y measure the degree of uncertainty about current Y resolved by past Y. And the mutual information among current Y, past X, and the past Y measure the degree of uncertainty about the current Y resolved by past X, however, already resolved by Y's own past. We are interested in how much uncertainty of Y resolved only by past X. So we subtract the mutual information among current Y, past X, and past Y from the mutual information between current Y and past Y. So left is shown as this triangle-like region. It measures the degree of uncertainty about the current y resolved by past x individually. So this is the transfer entropy from x to y. Transfer entropy is first introduced by Thomas Schreiber in 2000. To calculate the transfer entropy, we need to estimate the joint probability and the conditional probability as shown in the equation. For example, we have two time series data of x and y, and in our example, x represents the climate index or the sea surface temperature anomalies, and y represents the precipitation, for example, at Berkeley. So the yellow cell here is the current value of y, and the green cell is the past value of y, and the red cell is the past value of x. The colored cells are called computational window. By moving the computational window along with the time, and we record our values pair, and we could estimate the joint distribution and the partial distribution from the matrix. Then estimate the joint probability and the conditional probability to calculate the transfer entropy from x to y. So here is the moving computational window in this case. To establish the statistical significance of the measured coupling, that is, whether or not a coupling is significantly stronger than that which could occur through randomly chance between unrelated time series, the method of shuffled circuit is used. To estimate the shuffled circuit transfer entropy, the value of the time series are shuffled randomly in time to destroy the time correlation between them. We shuffle the data for 100 times to estimate the distribution of shuffled transfer entropy, and a one-tailed hypothesis test is applied to determine the significance and evaluate the significant value level. And meanwhile, we are interested in how long it will take for x to affect y. So in other words, what is the time lag from x to y? We introduce a new parameter tau here. Tau is the distance from past x to y in time axis. Here is the moving computational window when tau equals to 1, which measures that x will immediately affect y. And here's the case that tau equals 2 and 3. So we will test tau over a wide range of possible values and calculate the transfer entropy for each one, like the method mentioned in previous slide, and pick the one with who passed the significant test. And in some case, we need to take the time lag between current y and past y and the length of history into consideration. Here's an example of complete computational window. However, limited by the computational cost and data requirement, we have to make some assumptions. First, as most of the knowledge about current y is usually contained in the immediate history y, so we set the omega, which is the time lag between current y and the past y, as 1. Then the assumption that setting block length of history is conservatively biased, as it neglects the information transferred to current y with block length that the history of past x and past y greater than 1. However, it is commonly employed in practice to reduce the dimensionality of the probability distributions to 3-dimensional distributions to make them computational tractable. So in the following research, only the parameter about the time lags from x to y will be taken into consideration. So the transfer entropy have 5 major advantages comparing with the traditional correlation analysis. First, transfer entropy could be used to analyze the nonlinear relation between variables. Second, it could not only tell us the two variables are correlated, but also tell us the directionality of this impact. Third, it also shows the statistical significance. We could know what the probability that feedback we analyze is caused by real underlying mechanism or just by chance. Fourth, it could tell us the relative strength of the impact in terms of measuring how many percentage of uncertainty of y is resolved by other variables. Last, it also measures the time lag of the impact from one variable to another. By calculating the transfer entropy among the variables with a complex system, we are able to delineate the system with feedback process network shown on the left. The pink circle represents the information provider in most time, and the green one represents the information receiver. The thickness of the arrows represent the strength. So I will talk this in detail on the following slide. And we are also able to delineate how the system changes along with time or space. On the red figure is describing the feedback process network change along with time. Transfer entropy is a non-parameter statistical measurement, but we are also interested in quantitatively how the system or the variable determined by other variables. We introduced regression method as a next step analysis in my workflow. So first, let's start from the regular regression. As we know, the regression analysis is a statistical process for estimating the relation among variables. The least square regression measures the performance by calculating the residual sum of the square, and the counter of the residual sum of squares shown in the figure. The thicker the line, higher the residual sum of the square. And the blue point represents the best fit of the data we input. However, usually least square regression try too hard to best fit the input data and put a lot of effort to delineate the detail of the errors, which will lead the coefficient too far away from being generalizable. It is acceptable to sacrifice the bias to reduce the variance and to have an improvement in interpretation. By adding the penalty term of coefficient into consideration, we could reach our goal. So the blue region represents the penalty budget. The regression coefficient right now will fall at the intersection point between the counter and the region. In this case, the ridge regression makes sure the coefficient will not go too crazy to be not generalizable. However, some variables with minor effect in this system still have even very tiny coefficient. It is reasonable to have a sparse regression to help with understanding the system. So the robot Cipriani introduced the lasso regression in 1996. The penalty term of coefficient is no longer sum of square, but the sum of absolutely value. So the lasso represents the least absolute shrink and select operator, which changed the constraint region into a rectangular with vertex on the axis. These attributes will tend to set the coefficient of some variables with minor effect to 0. Now, after introducing transfer entropy and lasso regression, we are also interested in how these two statistical methods could work together. First, they both have the ability to do feature selection, or called variable selection. Lasso select the feature by setting the coefficient of unrelated predictor into 0, and the transfer entropy select the feature by evaluating the statistical significance level. But what if the results from both methods are inconsistent? If we have results showing higher impact in transfer entropy but low in lasso, which will indicate the nonlinear part of this variable should be taken into consideration. And if we have high in lasso but low in transfer entropy, which indicate the autocorrelation of the predictor should be taken into consideration. So in this case, comprehensive feature selection could significantly enhance the analysis. Meanwhile, given the result from the transfer entropy, it could help us to choose which variable we should take its nonlinear term into consideration. And given the significant time lags calculated from the transfer entropy, we could add variables shift according to the time lag and better improve the regression result. I implemented the method and workflow mentioned above onto 4 complex Earth systems over multi-spatial and temporal scale, as shown in the list. And And let's start from our example. So for this semi-global and decadal scale, we focus on analyzing the feedback between climate index to precipitation pattern in United States. So we take the climate index as variable X and precipitation as variable Y in the previous slide. And the preliminary result shows that the feedback process actually change along with location. We keep up the El Nino climate index series. We could see from the figures on the right, the red represents the region is significantly impacted by the climate index, and the precipitation pattern over the United States are changing along with the location of the climate index. And the method could not only be used to analyze the system changing along with the space, but also with time. For the global and the millennium scale, we analyze the feedback among the atmospheric variables like CO2, methane, dust, oxygen 18, and external variables like obliquity, eccentricity, precision, and solar radiation. So on the right hand is the figure that we delineate how these variables are interacting and what role do they play in the system. And on the right figure shows that the system is non-stationary. We could delineate how the system change along with time. So this is a co-work with the postdoc in our group, Chris, and the postdoc at LBNL, Zhu Qing. The method could not only used to analyze the time series data, but also could be used to analyze spatial data. The high spatial resolution data like LiDAR and remote sensing image offer a potential way to study geography questions in a novel way. Like in this region and the yearly scale, like in this regional and yearly scale problem, the research region is called Westlake Delta. It is one of very few delta regions that's growing in these years. We are curious about how vegetation contribution to this delta growth. To calculate the transfer entropy with data that intensive in space but sparse in time, we need to extend the method through in modifying computational window. And we classify the vegetation types from the high resolution remote sensing images, and it's from the satellites named Worldview 2 with 0.46 meter resolution. And this already been done by other scientists as well. Then we estimate the surrogate bell volume and topography from the high resolution LiDAR. Then we implement the spatial transfer entropy to analyze how different vegetation type modify the topography and how they are grown determined by the topography. And for the global and the decadal scale, we are interested in what the difference of carbon climate feedback in different region forests. So this is a co-work with Zhu Qing, so I'm not going to emphasize on the physical background of this research. And we compared the carbon climate feedback strengths at different ecosystems and found that actual tropic forests, mostly arboreal forests, is a critical region that is sensitive to climate warming. Further, the sensitivity likely comes from the soil respiration, which is a possible positive feedback and further warm up the climate system. In the GPP, RA, RH are all respond significant to temperature, but the RH is the strongest signal that feedback at the atmosphere and affect CO2 concentration that will subsequently affect land surface CO2. That's basically all we have right now. And here's the timeline of my study plan for the coming 2 years. And 2 of the 4 projects have finished the most of the analyzing part. And here's 3 of them already be written into draft. 1 of them is about to submit. Yeah. And that's all about my qualifying exam presentation. Thank you so much.